Hi, I'm Wouter from Triply, and this is the presentation for the EduSurf course where we will introduce GeoSPARQL. GeoSPARQL is an extension on top of SPARQL, and SPARQL is the standardized query language for linked data. Now, GeoSPARQL is sometimes referred to as one thing. To some extent that's true because it's one standard. It's been standardized by the Open Geospatial Consortium, or OGC. However, at the same time, GeoSPARQL consists of different components. So it's good to distinguish those a little bit, because otherwise it can be a little bit confusing when later in this presentation I will be talking about GeoSPARQL in different ways. So the biggest distinction within the GeoSPARQL standard itself is that GeoSPARQL refers to a set of terms, a vocabulary if you like, that you can use to represent geospatial knowledge in linked data, and that at the same time it also introduces extensions to the SPARQL query language. So it's both a representation extension for RDF and linked data, as well as also an extension to the SPARQL query language. Now, to be honest, it's even more than that, because the GeoSPARQL standard also contains additional reasoning rules. So that's extending upon RDFS, RDF schema, and it also includes some rule interchange, some rule-based components for rewriting geospatial queries. However, the last two components, so say the reasoning component and the rule rewriting component, are left out of this presentation altogether, because GeoSPARQL is a very big standard. It would be too much to cover it all in one presentation. Also, looking more from a practical point of view, I think that the reasoning capabilities and also the query rewriting capabilities or rule capabilities of GeoSPARQL are not that often used in practice, at least today. Maybe in the future they will be picked up a bit more, which is another reason why we will focus on the first two components of GeoSPARQL, that is representation and querying. Now, with respect to the representation part of GeoSPARQL, you've probably already played around a little bit with these representations in the part of the EduSurf course by Stanislav. However, I will also cover some of these representational aspects. If there is a little bit of an overlap, I think that doesn't really matter that much, and it might even be good because it makes it easier for you to transition from the representational part of the course to this more querying part of the course. The querying component of GeoSPARQL builds on top of SPARQL, and it's necessary to already be familiar with SPARQL before you follow this presentation. And this is why I put several episodes of my SPARQL tutorial in the EduSurf Moodle environment as well. So please go there first in order to become familiar with SPARQL in general, and then after that you come back to this presentation and you learn the GeoSPARQL additions on top of that. Now, it's also interesting to mention how GeoSPARQL was added to the SPARQL standard. So the SPARQL standard originally already contains the ability to specify new functions, new functionality, that is not part of, say, the core of SPARQL, but that can be specified in additional modules. And GeoSPARQL is an example of such a module. So GeoSPARQL also shows that it's easy to extend SPARQL, which is of course really nice because SPARQL does cover a lot of stuff. It allows you to query graphs, it allows you to filter things, to modify things with various functionalities. However, domain-specific operations, like in this case geospatial operations, are not a specialty of the W3C, the standardization organization for SPARQL. So it's very wise to allow modules from different domains to be specified, such that the SPARQL language can be enriched in such a way that it also becomes a viable tool within various domains, in this case the geospatial domain. Now, I've prepared a little presentation for you today. I'll go through the slides one by one, but I'll also sometimes dive into the more practical aspects of doing things. This is the technical component of the EduSurf course, So we also sometimes are allowed to make our hands a little bit dirty and look into queries themselves. So this slide formalizes a little bit what I already mentioned, namely that GeoSPARQL can be decomposed into different components that do slightly different things. So you can see here that number one is the core of GeoSPARQL, and that is where the most fundamental class of objects, say spatial objects, is defined. The core is very small, so we'll go through that really quickly, and all of the rest is building on top of that core. Then the second component is the geometry extension. This introduces the representation for geometries and also the querying abilities for geometries. So this is one of the two most important components that we will cover. And then the third point, this is the last point that we will cover in this presentation today, is the topology vocabulary extension, which allows you to also specify relationships between spatial objects and between geometries. Now there is also some geometry topology extensions. I will not cover them today. Neither will I cover what I already mentioned before, the RDFS entailment extension, nor the query rewrite extension. The reason for that is, again, it's a big standard, and I think overloading this presentation for you does not really help. It's best to first become familiar with the foundations of GeoSPARQL, the functionality that are also widely used today, and then maybe later, and say if you want to go for more advanced use of GeoSPARQL, you can dive into points 4, 5, and 6 yourself. Okay, so let's get started with this core component. I already mentioned the core component is really small, and you can see this is true. It only introduces two classes. It introduces the class spatial object and the class feature. Now I've made these classes and also later data type IOIs and properties clickable. So if you click on them, you actually go into a linked data browser. And the linked data browser shows you the view of how this class looks like in the GeoSPARQL vocabulary. So this is a spatial object. It's of type class. This is its identifier, so it's within the www.opengis.net namespace. And it has a description saying the class spatial object represents everything that can have a spatial representation. It is a superclass of feature and geometry. So spatial object is, say, the parent of two classes that we'll see in the next couple of slides. So the features and the geometries. So in GIS, traditionally, you can split all the objects into two classes. You have features, things that can have geometries, and you have the geometries themselves. And these are, of course, not exactly the same thing, because I, for instance, have a geolocation right now. You could describe my position with a longitude-latitude pair, but I am not identical to this longitude-latitude pair, of course. So I, in this case, would be the feature, and the longitude-latitude pair of my location would be the geometry, if that makes any sense. Very good. So then the spatial object would be on top of that. So both me and the geospatial location, the geometry, both of them would be also spatial objects. Now you can also see some other properties here, like who was the contributor, who added this class, the creator, it was created in a standard working group. When was this added? 2011, and some other properties. Yeah, also a preferred label or pref label. Okay, so the other thing that's introduced in the GeoSPARQL core, and I already briefly mentioned it as a subclass of spatial object, is GeoFeature. Let's take a brief look at that as well. And there it says this class represents the top level feature type. This class is equivalent to something else that's defined in ISO standard. And this is maybe, let's not dive into the specific ISO standard, that's far too detailed for, say, the more introductory level that we want to have today. However, it's important to note that most parts of GeoSPARQL are actually aligned to other standards. So that's also, of course, a result of the fact that the Open Geospatial Consortium has standardized GeoSPARQL. The OGC has a lot of experience with themselves creating various standards and also, of course, collaborating with other standardization organizations like ISO. So you will often see that concepts in GeoSPARQL are actually quite familiar, especially if you are working in the GIS field. You will often recognize parts of GeoSPARQL as being aligned with other standards, which is, of course, in general a good thing. I've also included here a link to the OGC Geo, which is where you can take a look at the GeoSPARQL vocabulary yourself. It's not so big, it's 518 statements or triples, so it's a fairly small vocabulary. Now let's go to the next slide. This is already the core, so you can see I did not lie to you before. The core is really, really small. Next one up, now we're introducing quite a lot of stuff, is the geometry extension. Now the geometry extension is where we introduce classes, properties, data type ARIs that allow us to represent and then later also query for the geometries of features. So it first introduces this class geometry. Let's read its definition. The class represents the top level geometry type. This class is equivalent to the UML class something something, also again aligned to an ISO standard. Now there are several properties, and so the properties are going to connect nodes, and the nodes can be of class feature or class geometry. So let's start out with the properties that belong to instances of class feature. So these are properties that feature nodes can have. So the first property of this kind has geometry. We can take a look at its definition. Let's see. A spatial representation for a given feature. So has geometry indeed is a property that applies to a feature. You can also see that it is a property, more specifically in OWL terminology. That's maybe going into details a bit too much, but in OWL it's an object property. Let's not pay too much attention to it. Most important is it's a property. And let's see whether there are some further specifications. So here you can see domain, and that is the RDFS domain property, and that indeed specifies feature. So that means that that formally specifies that has geometry must be applied to instances of type feature. Let's see, we also see a range over here, and range mentions geometry. And remember, you have features and geometries, so the has geometry property basically connects those two. So it starts in its domain at the feature, and it ends in its range at the geometry, like that. These things are always something you can look up. In linked data, all the terminology has IRIs, and if you dereference an IRI, so if you look up the IRI on the internet or if you look it up in the linked data browser, as I'm doing now, you always get a full formal description of what the property or class means. Now, next to a regular geometry, you can also specify a default geometry using the GeoHasDefault geometry property. And the reason for that is that one property often has multiple geometries. For instance, something can be measured multiple times. So you could maybe take the outline of a house. Maybe the outline of a house was measured twice, maybe with different precision, maybe on different dates, maybe by different people. Maybe one of the geometries is in 2D, while another geometry is in 3 dimensions. So there are various reasons actually why one feature might have multiple geometries. And if this is the case, it's of course nice to know, well, what's the default geometry? So what's the geometry that I would use if I do not have any particular application-specific requirements? So this is often used in practice to have something like a raw geometry, so a geometry that has very high fidelity, has lots and lots of coordinates, lots of detail, whereas the default geometry is often a generalization of the detailed or raw geometry, and that is where you are basically cutting some corners. However, this default geometry is often the geometry you want in, say, very generic applications. So if you want to show something on a map, if you want to use something in a web application, you do not typically want to download or calculate with this very detailed geometry. So then sometimes you would specify a default geometry to be, say, a generalization of the raw format. Now, another property that is introduced by this geometry extension of GeoSPARQL is geodimension. And geodimension is not a property of a feature, but is a property of a geometry. We can actually look this up to verify. So when I click on it, I open it in the Linked Data browser, and then I see it's defined as the topological dimension of this geometric object, which must be less than or equal to the coordinate dimension. Okay, and there's some domain-specific terminology in there as well. And let's take a look at the domain and the range. And indeed, the domain is geometry, so dimension does not apply to feature, it applies to a geometry. And you can also see the range, and the range is an integer, so the integer should indicate the number of dimensions. Now, there are two more properties, and these properties also belong to the geometry, and they relate the geometry to a serialization of that geometry. Now, what does it mean? Well, the geometry itself is sort of a conceptual thing. So the geometry is the thing, the location as it was measured by somebody on some date, on some time, at some time. That was maybe using 2 dimensions, 3 dimensions, etc. So it can contain lots of metadata. However, this geometry node is not identical to, say, the sequence of coordinates. So the sequence of coordinates would be in a serialization. And that means that the geometry must be related to that serialization in some specified way. The way in which it's specified in GeoSPARQL, the relationship between the geometry and the serialization, is with these two properties. And there you can basically choose between two common representation languages, either JML or WKT. So either geo markup language or well-known text. Both of these representation languages or serialization languages are also specified by the OGC themselves. So here they are basically reusing one of their, or actually 2 of their earlier standards. And you can use this property to relate the geometry to a JML or XML based serialization of its coordinates, and this for a well-known text variant. Nice. Now what goes along with that is that if we would use SJML or if we would use SWKT, then we must have some way of specifying how this sequence of coordinates is to be interpreted. Because a sequence of coordinates, we're going to store this in a literal, not in an IRI. The literal, if it only has a sequence of numbers, we do not know that it's a geospatial coordinate necessarily. So we also need a data type IRI, and the data type IRI will be part of the literal, and it will specify that we must interpret the string component, so the sequence of coordinates, that we must interpret it as a geospatial serialization. And for this, GeoSPARQL introduces 2 data type IRIs, JML literal and WKT literal. Again, these correspond to the last 2 properties that we talked about. Now there's one more category of things that is introduced in the geometry extension. As you can see, this is a very big part of the GeoSPARQL standard. So besides the classes, properties, data type IRIs that we already saw, the geometry extension also introduces functions. So these are things that you can use in SPARQL to calculate certain values. So if you think about this in terms of my SPARQL tutorial, you would use these functions inside a bind expression. So you could, for instance, let's take the first one as an example here, geof distance. you could use this GeoF, F stands for function there, distance function, in a bind expression in order to calculate the distance between 2 points. So then the distance function would take 2 arguments. The arguments could be instantiated from a group pattern in your SPARQL query. And then at the end of the bind expression, you could say as variable, and then the variable would store the distance between the 2 points. Something similar can be done with intersection and boundary, but then you're not storing a distance, a numeric distance, but then you're actually storing a new shape, a new geospatial form, because then you're basically storing the intersection of 2 existing geometries. And boundary is something similar, but that is more or less a transformation from, say, a polygon to a line, and then the line would be exactly denoting the boundary of that polygon. Now, this is a lot of stuff that is introduced in this geometry extension. So that means that it's definitely time now for a couple of examples. So let's start out with a representation example. So how would we use this terminology that is introduced in the previous 2 slides in order to represent some of our own data? So in this picture you see a pictorial representation of a data model that I could actually use. So a representation that I could actually make use of given the GeoSPARQL terminology. So I could represent, this is a building of Kadaster, the Dutch land measuring agency. So this building would have a node in the knowledge graph. It would be represented in linked data, and that would basically be the feature. So the building would not be identical to the geometry. No, the building would be of type building and would be a feature. Then this feature can have a has geometry relation like this, and that means that this node will be a geometry. And you see I'm using the underscore notation here, which means the geometry is a blank node. That's a detail that's not specific to GeoSPARQL, and it's not particularly important here. It basically means that we did not assign an IRI to the geometry, but what's called a blank node, which is done with this underscore syntax. Okay, so the feature has a geometry like this. And you can see on the right hand side it also has a second geometry, and this is possible. As we already mentioned, one feature often has multiple geometries. Now this geometry on the left hand side is specified with 3 properties. Let's go through them one by one. So you have the SJML, which links the geometry to a serialization in JML, and you can already recognize that a bit because you see this XML-like syntax here. It can have a GeoSWKT, so here it has a well-known text serialization. If you've seen well-known text before, then you also recognize this as typical well-known text syntax. And it also has a geodimension, and remember, a geodimension needs to have an integer value. So in this case it's a 2-dimensional geometry. But we also have a geometry on this end, on the right hand side. And this is specified with the same properties as JML, SWKT and dimension, but this is a 3-dimensional geometry. And you can also see this in the JML serialization and also in the WKT serialization. That is, 3rd dimension is also taken into consideration when serializing the actual coordinates. Now, what you can see is that GeoSPARQL is purposefully very generic. You're free to model things in whichever way you want. You can have 2D shapes, you can have 3D shapes, you can have both. You can use JML for serializing, you can use WKT for serializing, you can again use both. And there are several other ways in which you can make this even more complex, because we did not even cover all of the terminology that is introduced by the geometry extension. So actually, let's go back 2 slides. So whenever I use these 3 dots, I did not mention this before, but whenever I use these 3 dots, it means that there are more properties that I'm not covering in this particular presentation, but that are part of the GeoSPARQL standard. And there's also more functions, as you can see. Okay. Now, this is already making things a little bit more concrete, because here we can see pictorially how the data representation would look like, but nothing beats actual data, actual examples. So let's go look at a Dutch building. This is published by Kadaster as part of the base registry of buildings, Bach. That's one of the key registries in the Netherlands. And what we see here, we have an identifier here, and this identifier also has a unique IRI over here. And this is identifying the building of the football stadium of Ajax, which is one of the more famous soccer teams in the Netherlands. So you can also see there, and this is where the grass is, where they would play soccer. The road actually goes underneath, so it's not going over the soccer field as is maybe suggested on the map here. This is OpenStreetMaps. We also have the classes to which this football stadium belongs. One of them is called pand, which is the Dutch word for building. And the other one is GeoSPARQL feature that we already covered. And as you can see, it also has several properties. This is the property that we are most interested in right now, because this is using the has geometry property from the GeoSPARQL vocabulary. And we can also click on its object value, and then we get the unique identifier of the geometry. And then this geometry also has a property called GeoSPARQL SWKT, and indeed the value of that property is a well-known text literal. If I hover over this literal, you can also see its data type IRI, WKT literal. And when I click on the ellipsis, I can also show the full value. And this is of course quite lengthy, quite a long literal, because this building has lots of strange little corners. Now in the breadcrumb, you can actually see that we started out with this building in the Dutch key registry. And then we traversed using the GeoSPARQL has geometry property to the geometry. And then finally, that geometry also has a SWKT literal. Now I must apologize a little bit for the use of Dutch terminology. Now the reason for this is that the key registry is a crucial component of the Dutch government. And this means that the concepts that are used in this linked dataset have to be closely aligned with the Dutch law. So because this data is used to determine ownership of property, the transfer of ownership, but also the taxation of ownership. These are all things that are important components of Dutch society. So that's the reason why it's not easy to have English translations, because the Dutch word is used in the Dutch law, and that's where the vocabulary has to be as closely aligned to as possible. However, it's only a couple of Dutch words that you will see in these example queries, so I will give you the rough English translations. So I hope these Dutch words will not be that much of a problem to you. So let's go back to the slide. Okay, so we now saw a concrete example of a data set that was actually using the feature geometry distinction, and then also the has geometry relation, and also the geometry serialization distinction, and then the SWKT property. So this is the core representation introduced by GeoSPARQL. Let's now look into a concrete GeoSPARQL query. So this is a GeoSPARQL query in which we are going to retrieve the geometries that we have just described in terms of their representation. This query is only using components that were thoroughly introduced in the SPARQL tutorial episodes that I have also included in this Moodle. So if there's anything in this query that you do not understand, please first go back to those SPARQL tutorial episodes and then later return, because you should be able to understand this query fully. I'll go through it very briefly in terms of what I already explained in the SPARQL tutorial parts, but it might allow you to connect the two parts of this course together a bit more. So this is the prologue, that's the introducing some prefix abbreviations that we will use throughout the rest of the query. This is the projection, so this is determining how the table will look like that's coming from performing this SPARQL query. It will have two columns, a feature column and a shape column. This keyword denotes it's a select query, so that indicates that we will be pattern matching the knowledge graph and returning a tabular format. This is the pattern of the query, and more specifically this is a group pattern that consists of three triple patterns, triple pattern 1, triple pattern 2 and triple pattern 3. The semicolon indicates that we've left out the feature subject term over here, and this A abbreviates the RDF type relationship. Finally, there's this modifier at the end which specifies limit 1, that we will only be returning one row in our result table. Now let's click on run this query, and this is actually something you can do yourself. I'll include this presentation as a PDF file in the Moodle environment, and in this PDF file you can simply click on all the links and run all these queries yourself. So let's run the query, and then we see the result over here on the map. So what does this show us? This shows us an arbitrary building, an arbitrary pand in Dutch terminology, in the Netherlands, somewhere in the Netherlands. Let's verify it's really in the Netherlands by zooming out a couple of times more. Yes, this is in the southern part of the Netherlands, as you can see. I can also zoom, but then I have to click, I have to hold the control button. Like that, that's very easy. That's maybe easier than clicking very often. Nice, okay. So this is an arbitrary building in the Netherlands. Now what happens if I change this to limit 2? Then I will get back 2 results in my results table. And now they are a bit difficult to find on the map, but I can choose between different modes of visualization here. And if I click on the heat map, then it's easier to find the second result. So the second result is over there, and I can go back to normal, and there I see the actual polygon. Now I can also do limit 200. Let's see what happens. Yeah, there you can see some of these buildings. Again, with heat map it's easier to see. Let's maybe zoom in a little bit over there. So I have a couple of buildings over here. Indeed. Nice. Okay. So this is a very simple query, and it returns features and their corresponding shapes, and the features must be instances of Bach pand. In other words, they must be represented as buildings in the key registry of buildings in the Dutch government dataset. Now this is a very simple SPARQL query, but it already shows you that even with very simple SPARQL queries, only a couple of lines, you can already be using GeoSPARQL. In the next queries I will show you some more advanced functionality. Those queries will also become a little bit more difficult to read. They will be using more specialized functionalities. However, there is nothing stopping anybody from using these relatively simple queries to at least already retrieve geospatial information in a fully standards compliant way using linked data and GeoSPARQL. Now in this query I'm first going to introduce a little bit of abbreviating terminology that allows us to write these SPARQL queries in a more simplified way, because otherwise the next SPARQL query will be a little bit too complex to show on one screen. So I'll introduce 3 forms of further abbreviation. First of all, I'm going to use the star in order to specify what's called the generic projection. And this means that all of the variables that are visible within the pattern, the underlying pattern of the query, will be automatically added to the projection. The only caveat here is that the order in which the variables will be added to the projection is unspecified. So this means that the client application must not expect things to be in the 3rd column, because the 3rd column doesn't mean anything when you use the stars. Now we use this to automatically return all the visible variables. In this case that's only the shape variable. The second abbreviation that I want to introduce is these square brackets. And you can see that the square bracket here is replacing the feature variable. Let's briefly go back to the original query. So the feature variable is no longer there. And that is exactly what this notation allows us to do. We also have to close the square bracket at the end of the group pattern. So I also have it specified here. So if you do opening bracket, predicate object, closing bracket, then you've basically introduced an anonymous subject term. That's called an anonymous node, like that. And then the third and last abbreviation is this forward slash. Let's see how it's done in the original query. There we have a geometry, and then we reuse the geometry here in order to get the actual shape. But we are not returning the geometry in the projection. So in other words, the geometry is a little bit of an idle wheel here. It's only there to sort of connect together the has geometry and the SWKT properties. But the binding of the geometry variable itself is not actively used. And what this means is that we might as well remove it from the query, and then the query becomes a little bit shorter. Other than that, the query also becomes easier to maintain, because if I'm now modifying one of these two geometry variables in the previous query, the query might become inconsistent because I also have to modify the other occurrences of the same variable. And this is a little bit of a maintenance overhead. So using the forward slash notation, as I'm doing here, is actually a way of also simplifying your long-term maintenance of SPARQL queries. Now, with these three modifications or three abbreviations, so with the generic projection star, with the anonymous node square brackets, and with the forward slash abbreviation, we have exactly the same query, returning us exactly the same result. So again, an arbitrary building in the Netherlands. However, we can do so with a significantly shorter and easier to maintain query. Now we're ready to go to the next query, where we use all of these abbreviations several times. And this is a more complex SPARQL query. So I would not think bad of you now if you find this SPARQL query relatively difficult to process and to interpret. First of all, it's using the key registry of the Dutch government, which means that its terminology is in the Dutch language. And also this uses a level of nesting that you have not seen before, also not in my SPARQL tutorial. However, I would still want to include this SPARQL query because I think it's nice to have something that shows you a real-world application of GeoSPARQL. This SPARQL query is actually querying the production system of the Dutch Land Measuring Agency, or Kadaster. And this is actually allows you to retrieve all of the buildings that are officially registered in the Netherlands. And this is of course really nice, that GeoSPARQL is really used in production environments. Now let's take a look at this query. So we have a place of residence over here. I filled it in with a literal named Amsterdam. We have a public space that's filled in with de Boelelaan, which is the name of a street. We have a house number over here, now house number 1105, and we have a postal code or zip code, which I've also instantiated with a specific literal. And then here we have a geospatial shape. Now the other parts of the query that I did not mention explicitly and that I also did not highlight are parts of the query that you do not necessarily need to understand. This is a relatively difficult data model, which is necessary because in Dutch law they make a distinction between a building, an address that is maybe inside the building. Maybe one building has multiple addresses because there could be multiple apartments in a flat, for instance. You also have the distinction between the public space, which could be a street, but a square could also be a public space, for instance. And then you also have the relationship to the place of residence. So this is conceptually speaking already rather complex, and that's the reason why this query becomes a little bit longer. However, you can still click on the link to run this query. And one of the best ways to get to know SPARQL is to modify existing queries. So you do not always need to fully understand every SPARQL query, as long as you can run it yourself, in this case in TripleDB, in your GUI, or maybe in your own environment. Run these SPARQL queries yourself, modify them, and that's one of the best ways to learn more about any formal topic actually. Now let's scroll down a bit. What this retrieves is a specific building in the Netherlands, and this is the main building of the VU University Amsterdam, which is the university that Triply is located at. Triply is located somewhere over here on the same campus, but this is the main building. And let's take a look at this SPARQL query. So let's see what's a nice way of modifying this query to get back some different results and to get a little bit more of a feel of how this query actually works. So I could go to this house number and I could replace it with a variable called number. And this basically means that while in the original query I retrieved one specific building, now I will be retrieving multiple buildings, namely all buildings that share the same street name, place of residence and zip code, but they may have different house numbers. So let's take a look. When we run this query, you can see that we get various buildings that are closely related to each other. They are all on the same street name, and this is the original result. This is the main building, and these are some of the other buildings. This is the building where Triply is located. Now let's see if we can do this one more time. So let's see if we can maybe also remove the zip code and replace it with a variable. And then we should be getting all buildings that are located on this same street. You can see I get many results over here because that's mostly probably several apartments within the same building. And you can also see I only get 100 results, so I can actually remove this limit. And then I get back all the results. Let's see, 478 results. It takes less than 0.1 second for SPARQL to return this. And then I get all of the buildings on this road. There's a couple more over here. Okay. Now let's do one more generalization. Let's see whether maybe we can also do this street name as a variable. And then you can see that it takes a little while to load. And the reason for this is actually not SPARQL. SPARQL is generally very fast, at least modern SPARQL implementations, when they are configured correctly, actually have very good performance. It's mostly the browser that has some difficulty in putting all the things on the map. So now it's done. We can see that we have 10,000 buildings in Amsterdam. SPARQL returned this in 0.3 seconds, but the couple of seconds more that it took was for Leaflet in the browser to properly render all of this. Let's zoom in a little bit. This looks about right, so these are all buildings. Now I can do something that I also did in the SPARQL tutorial, in which I was binding some additional information for human display to an RDF HTML literal. I can do that here as well. Then I have to first introduce the RDF prefix, and then in bind I can create a strdt, string-based data type, where I can concatenate a couple of strings, and then also specify the data type IRI RDF HTML, and then bind that to a variable called shape label. This shape label variable must correspond with this shape variable, and that will align a shape with a label that you can see when you click on the shape. Now what do we want to display? Let's see, maybe start out with the street name, then let's do a space, and then let's do the house number. However, the house number is not a string, it's an integer, or it's a number at least. So we must do the string function surrounding it in order to extract the string component. And then I want to have a comma in the space, and then I want to have the zip code. And the zip code is a simple string again, so there I don't need the str function for that. Let's run this. Again, it takes a little while, mostly because of the browser needing to render. Let's see, we will also get back again 10,000 results. By the way, the reason why we get 10,000 results is this is a server setting. So you can configure on the server side what is the maximum number of results that one single SPARQL query should return. And if you're returning far more than 10,000 results, you can actually see the browser is already quite slow now. So returning, say, 100,000 results or maybe even millions of results is generally not wise, because most client applications, including most web browsers, will just not be able to process all of that information. So you can make this limit arbitrarily high if you configure your own server. However, it is most of the time not the best way to interact with client applications. If a client wants to retrieve more than 10,000 results, that's fine. And then the client should use some form of pagination to retrieve those results in different batches. Okay, this looks similar to when we ran the query previously. But now when I click on a building, I can see its address. This is a little bit of a visualization layer, so all triple stores are able to return this table. So all triple stores are able to return this RDF HTML literal. But in TripleDB we also have this visualization layer that allows you to put these things on a map. Okay, so this is a very interesting query. It's also a relatively complex query, so don't be afraid if you don't understand all of its components. Just try to run the query and try to modify it yourself. That's a great way of getting to learn more about GeoSPARQL. Now in our next query, we build a little bit more on top of the previous query, because in the previous query we already saw that we specified a shape label. And this shape label was subsequently used when you were clicking on a label. When you were clicking on a shape, it was displaying this label. It's also possible to specify the height and the color. And again, this is what the triple icon indicates. These things are specifically interpreted by TripleDB. All triple stores are able to return bindings to those variables, but only in TripleDB will you have this, say, visual layer. So what you're learning here is still generically applicable. It's just that not all triple stores have the same advanced level of visualization yet. Now let's run this query. It's very similar to the one we ran previously. We still have the same university building, but now we have specified that it has a certain height. Let's see in the table. So we've specified now this is the shape. It's a polygon in well-known text. But we've also specified a shape color, in this case the word green, and also a shape height. In this case it's 60 meters high. And we can also comment out this house number so that we will get multiple buildings and put them on the 3D map. And now you see all these buildings are 60 meters high and they are all green. And for visualization, this is just using the browser. It's an open source library called Cesium. There's a little bit of a mistake there maybe. And there as well maybe. So what you see here is that these buildings are not really fully 3D. So there are no rooftops, for instance. And this is a little bit of a lack in terms of the data. So we now have the standards to specify also 3D geometries. GeoSPARQL supports this. Well-known text supports this. The JML serialization format also supports 3 dimensions. However, it's still the data that is lacking here. So there are not enough governmental agencies yet publishing their open 3D data, which is a little bit of a shame. So the tooling is there now, and it would really be nice if in the foreseeable future we would see more open data, more linked open data published with actual 3D geometries with more detail. Now this green color is a little bit of a toy example, of course. All buildings are green. Well, that's not really a useful use of a color in geospatial terms. So in this query I have used colors in a more productive way to to visualize a gradient scale, and it's showing the number of corona infections in the Netherlands. Let's run this query. You can also run it yourself by clicking on the link. And this is a very complex SPARQL query, because what it does is it first is going to extract the maximum number of infections in the Netherlands, as well as the minimum number of infections. And then it's retrieving for each municipality the number of infections. And then in the end, it is combining those. So then it takes the number of infections over here, and then it subtracts the minimum number of infections, and then it divides it by the delta between the maximum and the minimum number of infections. So this is a little bit of a convoluted way of explaining, but what it basically does is it normalizes the number of infections for each municipality in the Netherlands to a value between 0.0 and 1.0. So the municipality with least infections will receive a normalized value of 0. The municipality with most infections will receive a normalized value of 1. And all the other municipalities will be somewhere in between. So they will have values like 0.15 or 0.76. And that makes it easy to visualize things on an easy scale between 0 and 1. So this normalized value between 0 and 1 is then reused at the top of the SPARQL query. It's actually concatenated here with jet, and jet is one of the color maps that is supported in DB. Let's see how it's returning this in the table. So in the table you get a polygon for a municipality in the Netherlands. You get a color, and this color is to be interpreted in the jet scale, but the important thing is of course this normalized value. You can also see that we multiply the normalized value with a number in order to extract a height, and this means that not only will municipalities with more infections have a warmer color, so they will be yellow or red, but they will also have a higher polygon. And finally, there's also a shape label that will specify the exact number of infections. So let's see this in the 3D environment. By the way, this SPARQL query takes 0.2 seconds, so that's not too long. It has 355 municipalities to display, and then the rest is the browser having to catch up with the data and having to display it accordingly. You see, these are the municipalities like Bernheese and also Landert, and here Nunspeet, where the number of infections is highest. And you also see some municipalities over here where the infections is relatively low. Of course, each infection is one too many, but still, relatively speaking, the number of infections here is low. And this is an example where you can use the color variable. You can also visualize the same thing in a 2D map, and it looks more or less the same. You also still have a good overview of the municipalities where the number of infections is relatively high. Okay, so these are a couple of SPARQL queries. We saw a very simple one, which was just retrieving some building with a shape. Then we saw a very complex query with the number of corona infections for each municipality. And in between we saw a more or less average level SPARQL query, which was retrieving information from the Dutch key registry using the official data model of the key registry. Now, looking back at these GeoSPARQL components that I introduced in the beginning, I promised you to cover the core, which was very brief, the geometry extension, which was very big, a vast section of the GeoSPARQL standard, but I also promised you to cover the topology vocabulary extension. So that's the thing that we will look at now at the end of this presentation. So let's go there. The topology vocabulary extension consists of properties that you can add in your linked data representation in order to explicitly relate features to one another based on their geospatial relationship. Let's take a look at a couple of examples. So we have the SF equals property, disjoint, intersects, touches, within, contains, overlaps, and also crosses. These all start with the letters SF, and these letters stand for simple features. You can see that I have included the 3 dots, which means there are actually more properties in the GeoSPARQL standard, but those are not simple features, those are Egenhofer and RCC properties. We will not be covering them today, but just for your information, there are even more properties in this topology vocabulary extension that are part of GeoSPARQL. Now I'll show you some of these. I'll show you this one in particular, the simple features within property. I'll show this in practice because we have a data set over here from the Dutch Statistics Office, and let's go over there. And this is an interesting data set. It shows you statistics for municipalities and neighborhoods in the Netherlands between 2017 and 2019. And we can go to the municipality that contains the university building that I showed you earlier. This is called the VU kwartier, so the Free University or VU University quarters. And this is in Dutch of type neighborhood. Buurt means neighborhood in Dutch. This is the unique identifier, or IRI, identifying this neighborhood. And as you can see, it has a GeoSPARQL geometry. We can click on it, and then it has a WKT, well-known text serialization. We already saw this earlier for buildings, but the same is true for, say, these neighborhoods. Let's go back. But it also has a SF within property, and that's the thing that we're interested in now, because this relates one neighborhood to a larger neighborhood in which the smaller neighborhood is located. Now this larger neighborhood is called Zuidas. We can click on it, and this is indeed a wijk. A wijk is another Dutch word for neighborhood, say a larger neighborhood. And you can see that the polygon that we had before was this museum quarters over here. And now we have a much larger shape. And you can also see it here in the breadcrumb. So we started out in the VU quarter, and that had a geospatial within relationship with this Zuidas neighborhood. Now this Zuidas neighborhood again has its own geometry using GeoSPARQL, of course. And this is SF within Amsterdam, because this larger neighborhood is contained within the municipality of Amsterdam. So let's click on that. And this is a very big geometry. So this shows you the full geometry of the municipality of Amsterdam. This is actually a multi-polygon because it also has this second polygon which is disconnected from the main polygon. Let's actually take a look, because if we follow the Hess geometry relation, we should be able to see this. There we can see that this polygon is actually a multi-polygon in well-known text. Nice. Let's go back to Amsterdam now. And Amsterdam is within the Netherlands, so this is the identifier which represents the entire Netherlands, but let's not go to that high level. What's most important for us now is to see that this smaller neighborhood, VU quarters, was within this larger neighborhood called Zuidas, and that was part of the city of Amsterdam. As a matter of fact, if I look here in the map, I may be able to find Zuidas somewhere over here. So this is where the university quarter was, and this is the Zuidas region. May be able to recognize it from these two pictures. So that is a very concrete example of how the Dutch Statistics Office is using this within feature to represent the containment of these different neighborhoods and municipalities. Now, this has very interesting use cases actually, because you have very detailed statistics on a low level. So you know various statistics like how many people are living in each neighborhood, what are the crime statistics there, how many cars are owned there, what's the average income, what's the average value of houses, how much gas and electricity is spent in these neighborhoods. And as a statistician, you can pull all of those statistics out, but what you can also do is you can also use the geospatial within relationships in order to aggregate those statistics. So you can say, show me electricity consumption at the level of the municipalities, at the level of the neighborhoods, so at the lowest level. But then if you want to also quantify it or visualize it on the municipality level, maybe you want to compare different municipalities with one another, you can just summate, aggregate or calculate the average by combining all of the neighborhoods that are contained within the same municipality. And you can do this based on geometry, of course, geospatially see what lies within which shape lies within which other shape, as you would do in GIS software. But you can also use the SF within relationship in order to write that in your SPARQL query. Now, this was only showing you one of the topology vocabulary extensions, but I hope that you have gotten a feel for how the others would work. And so you could also specify these other topological relationships. They work in a similar way as the within relation works. Thank you for your attention. This was quite a deep dive in GeoSPARQL, to be honest. I hope that if you first take the SPARQL tutorial videos and then do this more advanced presentation, that you're then able to at least make a head start by using GeoSPARQL. GeoSPARQL is very powerful technology. It has lots of features that I did not cover today. It can actually be used in production systems, as we are doing successfully at the Dutch Land Measuring Agency of the Netherlands, the Kadaster. I think GeoSPARQL is a very powerful technology. It does not only allow you to extract things based on their geometry, as more traditional GIS web interfaces already allow you to do, but it also allows you to specify your own criteria. If you only want to retrieve buildings in the Netherlands that were built before 1900, you can actually specify this. If you only want to retrieve statistics for municipalities with over 1,000 inhabitants, you can actually specify those selection criteria. That makes it a very valuable technology, but also a very complex technology. And that's the reason why GeoSPARQL can also be used to build simpler REST APIs or maybe GraphQL APIs. So it can also be used under the hood in order to configure your simpler APIs that you then supply to your consumers. I have also a couple of questions in the questionnaire that you will receive later, and the correct answers to those questions are actually sprinkled throughout my presentation and throughout my SPARQL training episodes. So if you watch all of them carefully, you should be able to answer those questions all correctly. I hope that you will be able to use GeoSPARQL in your own organization as well, because linked data becomes more powerful when more people are using it. Because when more people are using it, more organizations are able to link to each other and to reuse each other's knowledge. And it's only when you combine knowledge that you are able to extract new applications and that you're able to solve new problems.